Okay, so this is going to be sort of a long and complicated. We're going to be looking at linear second order homogeneous differential equations, and they're going to take the form where A, B, and C are just constants. So this is just what I'm going to be doing in this video. And they're linear because each term is just raised to the first power. There's no squareds or square roots in there. They're second order because they contain second derivatives. They're homogeneous because they're equal to 0. And they're differential equations because they contain derivatives. Okay. So before we get going, let's just dive in and show that you guys already know a thing or two about that. And I'm going to give you an example here. So if you watched a previous video, you should be able to come up with a function that's going to solve this equation. So hit pause and think about it. I'm going to rewrite this as and just like a previous video, we've got a function whose second derivative is equal to that function. Well, think about that. Okay, so if you said y is equal to e to the x, you're going to be partially correct. Okay? Because the first derivative of that is e to the x. The second derivative of that is also e to the x. And so we're going to get e to the x minus e to the x equals 0, and that works just fine. Okay, why did I say that's partially part of it? Okay, some of you are going to say that there's a c on there. Good, but you're not done yet. Can you think of another function that's going to also solve it? Okay, the other function is that you've got e to the negative x is also going to solve that, because the derivative of that is going to be negative e to the negative x, and then the second derivative is going to be negative times negative, which is positive e to the negative x. And so then that's going to also solve, and then you've got another c2 there as well. So you've got two. You got c1 e to the x plus c2 e to the negative x is the solution to that. Okay? Now, let's look at this one. Okay, so d squared y dx squared plus y is equal to 0. Now, you go, oh, well, I just do, this was e to the x, so then this one's also e to the negative x, but wait a second, e to the negative x solved that one. If I take the first derivative, I make it negative. If I take the second derivative, it comes back to be positive. That plus that. So e to the x and e to the negative x is not going to work in this case. So think about what other function, there's some simple functions you can think of that would solve that. Okay? Well, if you thought about it, you might have come up with y equals sine x. Because y equals sine x, y prime is equal to cosine x, and y double prime is equal to negative sine x. Okay? So there you got. That we have the second derivative is the negative of the first derivative, so that's going to work. So that's part of a solution. Okay, but it's not the whole solution. Why? Well, once again, yes, you could multiply that by any constant. That would work. And then some of you've already sort of getting the feel of it. So you should probably also know that there's another part to this. Just like there's two parts to that, there's two parts to this. That cosine x also does the exact same thing. That the first derivative is negative sine x, second derivative negative cosine x, and there you go. Okay, now, if you're thinking, if you're really thinking, there's another solution to this as well that involves e's. So, e to the what, y equals e to the what, y double prime is equal to negative e to the what. Okay. Well, that one is going to be, I'm going to reveal it now, c1 e to the ix plus c2 e to the negative ix. Because e to the ix gives y prime is I e to the ix, which gives y double prime is going to be I squared e to the ix, which is negative 1 e to the ix. And then e to the negative ix is going to do the same thing, and multiplying by constants is going to do the same thing. So what I want you to think about is if I've got, so there's a few things that I want you to think about related to that. One is if I've got x squared minus 1 equals 0, that factors into, that gives me factors of x equals plus 1 or negative 1. So that's this one right up here. If I've got x squared plus 1, the roots of that are going to be x equals plus I and minus I. So in this case, I've got basically x squared minus 1, and I look for the factors of that. And here I've got x squared plus 1, and I look for the factors of that. Okay, and then the last thing that I want to say on this page before I this is a long involved video, but I'm just going to, before I move on to some specific information, is formula. Is that e to the ix is equal to cosine x plus I sine x. So if you sort of think about that, I'm not going to really get into it. It's a little bit beyond me. But these two solutions are related by Euler's formula right there, which is a really remarkable formula. Okay, so now what do I want to say? Let's just get into some specifics here. We're going to have a d squared y dx squared plus b dy dx plus c is equal to 0. And we're going to have three cases. We're going to have three solutions. Case 1, we're going to say that b squared minus 4ac is greater than 0. case 2, b squared minus 4ac is equal to 0. Case 3, b squared minus 4ac, you got it, is less than 0. Okay, now this is going to look a lot like quadratic formula, and it will. So what we're going to do is we're going to say y equals c1 e to the s1 x plus c2 e to the s2x, where s1 is equal to negative b plus or minus square root of b squared minus 4ac over, just make it plus rather, sorry, over 2a. And then you're going to have s2 is equal to minus b minus square root of b squared minus 4ac over 2a. And there you go. So it's basically just the quadratic formula applied to this. Now, in a lot of books, you're going to see in a lot of books that it's just, they omit that a. So it's just second derivative of x, second derivative plus b times the first derivative plus cy, I forgot that y there, equals 0. And they're just going to omit the a. But you don't have to omit the a. You can just leave it right in there. And in which case you just get, you just leave it just like your regular quadratic formula, which by this time you've made some sort of peace with, otherwise you wouldn't really be on to calculus. Okay, then my case 2, well then this part here is equal to 0, so if b squared minus 4ac is equal to 0, I'm just going to get minus b over 2a, but I need to have two solutions, so my solutions are going to be c1 e to the sx plus c2x e to the sx, where s is equal to minus b over 2a. In case 3, I'm going to have an imaginary part, and that imaginary part is going to give rise to these sines and cosines. So what I'm going to do is I'm going to have y is equal to c1 e to the ux sine vx plus c2 e to the ux cosine vx, where u is equal to negative b over 2a, and v is equal to square root of 4ac minus b squared over 2a. Where I've just flipped the sign, in there, so that if b squared minus 4ac is less than 0, then 4ac minus b squared has got to be greater than 0, and so then this generates a real number. So let's come up with a couple of examples. Well, let's do 3 examples, right? The 3 examples that I want to do. Okay, I want to do, let's do d squared y dx squared plus 6 dy dx plus 9y is equal to 0. Okay, well, I do that my s's are equal to minus b plus or minus square root of b squared minus 4ac divided by 2a. So I'm going to get my s's are equal to minus 6 plus or minus square root of 6 squared minus 4 times 1 times 9 divided by 2 times 1 and I go s is equal to minus 6 plus or minus, that's 36 minus 36, that's 0 over 2. So I get s is equal to negative 3. Now if I think about it, if I had just factored that out, if I had done, well, what are we going to call it? Let's call it s squared plus 6s plus 9 equals 0. If I factor that out, I would have s plus 3 and s plus 3 equals 0, and that gives rise to s equals negative 3. So if I just took that, sort of made it into a quadratic and factored it, I would have done that without having to use the quadratic formula. Okay, so that's a case 2. So in that case, where's my case 2? There's my general formula, so my s is negative 3. So I've got y equals c1 e to the negative 3x plus c2 x e to the negative 3x. And I'm not going to do it right now, but you can show that if you take the first derivative of this and then take the second derivative of it and plug the second derivative in there plus 6 times the first derivative plus 9 times this formula, you're going to get 0. Okay, next one. 2 d squared y dx squared plus 5 dy dx plus 3y is equal to 0. Okay, well, let's think about that in terms of what we were just doing. Let's write it as 2s squared. Oh, I'll leave it as the cursive s, even though some people don't understand what that is. Can I factor that? So I sort of think about that for a second and I go, So it's like 2 and 1, 2 and 1, and like 3 and 3 and 1. 2s, everything's plus. So I've got, oh, wait a second. So I've got, that's going to be 2 times 3, that's 6, that's 7. How about if we do it this way? Okay, so now I've got my FOIL. So my first is 2s squared, my outside is 2s, my inside is 3s, that makes 5s, 3 and 1, that makes 1. So there, I got it. So now my factors here is s1 is going to be equal to negative 3 halves, and my s2 is equal to negative 1. And so that's a case 1. So y is equal to c1 e to the negative 3 halves x plus c2 e to the negative x. Okay, and you can probably guess what's coming last. Okay, let's do this one. Let's do d squared y dx squared plus 3 dy dx plus 4y is equal to 0. So my a is equal to 1, b is equal to 3, c is equal to, let's see, what do I want it to be? That's like, it's hard to make it anything, so let's just make it 4. That's fine. Okay, so now my s is going to be equal to negative 3 plus or minus b squared, which is 9, minus 4 times a, which is 1, times 4, which is 4, c, which is 4, over 2 times 1. So that's going to be negative 3 plus or minus 9 minus 16 over 2. So S is going to be equal to negative 3 plus or minus, give me a little bit more space. S is going to be equal negative 3 plus or minus square root of negative 7 over 2. So what I'm going to write that as is S1 is equal to negative 3 halves plus root 7 over 2i, and S2 is equal to negative 3 halves minus root 7 over 2i. And what I'm really going to say is I'm going to say that u is equal to negative 3 over 2, and v is equal to root 7 over 2. Because I'm sort of just showing you consistency, but that's a case 3. And so y is equal to c1 e to the negative 3 halves x sine of root 7 over 2x plus c2 e to the negative 3 halves x cosine root 7 over 2 times x. And that's that solution. Okay, and so that's what I have to say in that video. And then if you like that one, next one is going to be even crazier.